Hello, friends, and welcome to part 4 of our machine learning track, what's that house worth? It is our final day together, and I realized I have not put on the flower crown all week, and so I'm going to remedy that right now. Oh. My 2 flower crowns are tangled up. Okay, it's been freed. Boom. Now it's officially Global Hack Week. I hope you're doing well, and I hope you're ready for some serious machine learning. A couple notes as we just kind of vamp and wait until it's actually time to formally start off. One is, I think I called this out yesterday, but so much of machine learning is sort of the dirty prep work, right? I think I mentioned day 1 we were kind of being programmers, and then day 2 we were data scientists, and then day 3 we kind of actually got to do machine learning. And then today we just get to launch further and further into the machine learning of it all, right? We sort of dotted all our I's and crossed our T's as we pre-processed and cleaned our data. And now we get to just kind of run fast. The other note that I would put out there, so today, just a lot more machine learning, getting into it. The other thing that I would throw out is that also as we go further in the week, and I think this usually happens, is the further it is in the week, the less, I don't want to say the less prepared, but sort of the more specific and free-form things get, right? So like day 1 is, getting back into Python. That's like always the same. Day 2 is like, let's just analyze some data. That's, like you can put together some pretty graphics, and it's also, really relatively standard, right? What you're going to do the previous day is going to be the previous month is going to be pretty similar to what you do the following month. And then you get to sort of the last day and you're like, okay, what new novel thing can we throw out there? And I think this is actually nice for a couple of reasons. One is because you kind of discover the data alongside, the stream, but also because this is a lot closer to like the way that I just work, definitely day 1, that's like me performing intro to Python. And then by day 4, it's like, yeah, this is just me figuring things out, right? I think we got a little bit of this at the end of yesterday's stream, where it's like, oh yeah, the model is doing something kind of unexpected. Like, how are we going to figure that out? So a lot more of that today. I have published part 4, so I can send all the links in a second. Oh, that's interesting. Why is my screen is not showing up? Okay, you'll have to forgive me here. I'm going to have to figure out. Oh, there we are. Okay. We're back. OBS is being a little bit silly. But so I will drop all the links. So we obviously have our Kaggle competition, which is kind of the home base here. Dark Rules, good to see you. Good to see you. Welcome back. So there's the Kaggle competition, and then you can check in right here for part 4. And while we're just vamping, because I usually like to start like maybe 5 minutes after the hour, what are you drinking today? I am back at it. I think I'm coming full circle. I think the first stream we had this week, I was drinking some water, and then I didn't have time to eat dinner, and so I was doing another protein shake. So more whey protein for me. Dark Rules, are you drinking anything? You have some water, tea, or something? Alrighty. So definitely get checked in, get your credit. Maybe we can kick off before we really get into the thick of it. We can check back in with sort of our 3 tabs, our code tab. I saw a few other submissions. It looks like we have, so Random Forests is a user submission. Random Forest for Beginners Explain Cell by Cell. Very fun. And then House Worth. I actually haven't looked at this one. I think this one is newer. This looks like, okay, doing some novel. Ooh, okay, they do a different color per state. That's kind of fun. Some neat visualizations. Seems worth checking out. Lots of really awesome discussions. I really liked the sort of thread on what got you interested in machine learning. Oh, nanotubular, banana protein shake here too. There you go. it's just nice to press a button and just be like, I have dinner now. You know, it's nice just to kind of be done with it. So I respect that. I also enjoyed help someone else do some debugging or troubleshooting on getting a submission in, and then a very sweet recap of the week and what someone has learned. And a few others that I think I have not actually taken a look at. Did you know and transfer learning? So I'll take a look at those later. Our leaderboard continues to heat up. We have some folks with even better scores. So remember, our score here is on average, how wrong was your prediction? So here this is saying that on average, the prediction was around $53,000 away from the right answer. And so that's, starting to get to a point where you're kind of competitively predicting, what something costs, especially when a lot of these houses are, are 500, 600 grand, $50,000 off. Like, well, that's a lot of dollars in regular terms. When it comes to predicting the price of a house, it's not that bad. So that's really cool to see. We are going to see if we can get, as a stream today, see if we can get up there and see if we can do better. Dark Rules says, what is deadline time? Great question. Let's go back to overview. So it closes a day from now. It says August 4th. I'm actually kind of interested in why it doesn't give you like an actual time. I might regret pulling up this page because this is the host page. Okay, so here it is. Yeah, so it is the 4th, which I guess that is tomorrow. And me double checking that today is not the 4th. Today's the 3rd, right? Okay, yeah. So this is tomorrow, right before midnight UTC time. So you should still have, at least a solid 24 hours. Good deal. So yeah, maybe we jump into some code now. So that's in UTC time. Yeah, which actually, let's see, UTC time to PST. So 12 a.m. Oh, okay. So I guess it's a little bit less than 24 hours from now then. Yeah. Or it's about 24 hours from now. Okay, cool. That actually works out well. Yep. Right on. So a little recap. On the first day, we did our intro to Python. On our second day, we sort of did some exploratory data analysis and learned about some of the relationships in our data. On day 3, we took a look at sort of building simple models, some models that we could just code up ourselves from hand, like getting the average price per square foot and using that as our model. And then we also looked at using linear regression, right? And we looked at 2 things with linear regression. One was this idea that if you're doing linear regression, you can only capture relationships that are linear, right? You can't have like, oh, well, more square footage is more money up to a point, right? It's just, it's just a single line on square footage. And then we also looked at this idea of overfitting. If you give your model too many parameters and it doesn't have enough data to effectively train those, then it can get into kind of conspiracy theory mode and learn patterns that aren't really there. And the impact of this is that it will do worse on data it hasn't seen before. And we actually observed that, is that we were getting, in our own testing, we were getting, $50,000 of error. And then when we ran it on the test set, we jumped up to like $67,000. And so that was definitely a sort of a rude awakening, and it means that we have to be very careful about overfitting. So then for part 4, as I mentioned, this is a little bit more, this notebook right now is a little bit less fleshed out. But so I will, as we go through the stream, I will save and publish it so you can get access to, the new setup of code. But you should be able to navigate here and click copy and run, copy and edit. And our moment at the beginning here is pretty close to what we had yesterday. So mostly copied actually from part 2 where we did our cleaning. We are taking in our training and testing data. And so yesterday we looked at adding both zip code and city as different things that you could sort of assign prices to. And here I am just adding zip code and not city. The thought process was, well, maybe by adding both of those, we're getting a little bit of overfitting there. But we still convert our area into square feet. So if you remember the original data set, the lot area, so not the area inside the house, but the area outside the house of land, sometimes it was measured in acres and sometimes it was measured in square feet. So we just need to make sure those are all the same. Then in our pre-process script, we're dropping some of these things that we don't think are as important. Actually, you know what? I'm going to, instead of saying let's add zip code, what if we just added city? I'm going to edit this for reasons I will explain in a minute. So then we do our conversion. We merge in our information of, remember, instead of just having the state be one hot encoded, we replaced state with the average price from that state, with the intuition that some states are more expensive than others, and that's useful information for our model to have. And so we can throw that in, and then here instead of zip code we'll do city, and instead of zip code we'll do city. And that means we actually want to drop zip code here and then drop city down below. The final thing that I actually have in here is for all of the columns that are numerical, I'm actually right here calculating the z-score and removing things that are only keeping the things that are within 3 standard deviations. So this is actually a slightly more elegant way of doing our outlier removal that we did last time. So the intuition here is that if there are things in our data set that are really, really strange, right? Like there was one house that apparently had 14,000 rooms in it. And like, okay, maybe that means something, but probably there's nothing like that in the testing set. And so using this information is not actually going to help us generalize, right? So by removing that from the test set, maybe we can get a little bit more of a general model because it's not trying to fit to this one really random data point. And then finally, we can pre-process and our testing and training data. So this will start up our session. Oh, also another thing that I should just generically warn about, it is possible that I will have a UPS delivery during the stream. Unfortunately, it's one of those things that it's like, yeah, they tell you day of, like, yeah, we're coming by from 6 to 7 and you better be there. So I might take a brief intermission to go answer the door. I hope you will forgive me. And, oh, average prices by zip code. Oh, this should be by city. Polar Void isn't here to catch my typos before I run the code, Thank you for your flexibility, Dark Rules. Okay, so now we're going to do something that we did yesterday, but we're going to do it up front here. So remember, we're training our model on our training data, and then later we're going to run it on data it hasn't seen before. But because we don't actually have the labels for the data it hasn't seen before, there's actually no way. There's no way for us to know how well it does before we actually submit it. And that's kind of a limitation we'd like to overcome. So one thing that we can do is we can actually, before we train our model, we can save a little bit of that training data where we have the labels and use those essentially as our sort of fake test set. And so a phrase that I think I threw out yesterday, but we didn't use it in code, was a validation set. And so a validation set is the term that people will use for, well, this is not like the ultimate test of this model, but I'm using it so that as I'm developing, I can kind of figure out where I stand. Hey, Kaka Prague, good to see you. As always, lovely to have you here. So here we're starting our training and validation split early. Now you might say, hey, Will, like, shouldn't you be randomizing this and doing it 7 times? And the answer is, yeah, for sure, probably. But this is sort of a nice, simple way to get a little bit of a signal here. As you'll notice that for the X, which is our input, I am dropping the price. And then for our Y, I'm only keeping the price here. So our input will have everything except price, and our output will only have price. Okay. I actually really, really like this idea. And maybe because this session is going to be a little more freeform, maybe we do that as well. I really enjoy that idea. Grouping zip code or grouping cities that were small as other. Yeah. Or even I could imagine if it's small, like just defaulting to the state or something like that. Yeah, I like this. Okay, let's actually give this a shot. And I'm curious after I give it a shot, I'm curious how you ended up doing it. Okay, so something we could do is we could just start with our. Here, I'm gonna grab this down here just so we can play around a little bit, and then I'll put it up back into that cell. So we could do train, grab our city, and look at value counts. Cool. Okay, and then @more. @more only has one item, and so yeah, assigning any value to this like the usefulness of @more is probably silly, right? So we wouldn't actually want to say, well, the average value for @more is this. Whereas Anchorage, we have 300 things in there, so that that's maybe useful. I believe that this can actually function like a dictionary if we just index @more. Okay, great. So we can do our value counts. We could basically treat it like a dictionary. So we can say city counts. And then we could make a function that maybe accepts, maybe it accepts the whole row and then returns an average city value. So let's also grab, so here we just get the average price by city. And so let's see, get average city price. Boom. And so this will accept a row. And so what are we going to do? So the first thing we want to do is we can take that city and we can see how many times that city appears in our training set, right? And so we could say if city counts is greater than or equal to 10, so this is kind of what you were saying, is if our city shows up at least 10 times in our data set, then we can just say when we have average home prices by city, and actually I should just test this and make sure @more. Okay, yeah, that does work. We can just return the average price by city. Otherwise, we can return that. So this is sort of the normal case. If we have a decent number of data points on your city, we just give you the average city price. Otherwise, if it's not, so you could just say group them all together and say other. Another thing that you could default to is you could say, actually, just go to the state level. Just include the state because all of those cities should be in the same state. There should be sort of some overarching patterns there. So you could instead default to cities. So we could say if there aren't many records from that city, default to state. And you could say, hey, aren't we only already including the state price? Answer is yes, but this is sort of a way of just reinforcing, yeah, that state price is really all the information we have. So if city counts is greater than 10, return average city price. Otherwise, we can actually come up here and grab the prices by state. And we can return the row for state. Boom. Okay, so we can pull this metric back up here. So we have another little helper function. We can clean up these cells, but we do want to keep our city counts. And we can add that up by our other dictionaries. Great. Any questions about how we wrote this function or why we want this? I mean, we'll use it in a second, and hopefully that'll add some additional clarity. Cool. Okay, so this block where we merge, we can, instead of just merging that in, we can now apply our function. So I'm going to comment that out, and we can delete it in a second. So we can now say df. This is honestly in many ways cleaner already. Average city price is equal to df apply, and then we can apply our get average city price. And I believe we'll want to say axis equals 1. Let's see. Yeah, okay, cool. And that actually should just do it for us. and then we drop city and state. So let's run that and see. Oh, city is not defined. That's unfortunate. Why would city not be defined? Oh, city right here is not defined. We really should just be getting, yeah, because we're only accessing city through this dictionary of row. Okay, so this is a great question. Maybe I don't understand the syntax of the function. Won't it overwrite all the prices with the state mean? So it will in some cases. The idea here is if, unless I have a bug, what happens here is if this city shows up in our data set at least 10 times, then we will give the average price by city. So just the average in that city. But if there are less than 10 homes in that city in our data set, then we will use the average state price. So if this happens, then we'll already return this, and this will never run. You could also, like, I don't know if this is causing any confusion. You could also have this as an else, but like if we've already returned, we'll never run that. So kind of a style choice. This is a little bit nerdy, but I've been using Golang a little bit more, and Golang very much favors this, like, oh yeah, have a list of conditions where like you just bail out of the function if this is true. Shinto Noor, good to see you. Welcome, welcome. But as always, we need to actually test the code to see if it is doing what we want. So why don't we give this a run now? Oh, another issue. Key error, Churchton. Interesting. Oh, okay. This is actually a really good point. Is if the city isn't in our data set, so our dictionary we're only getting from our training set, but in the test set there could be new cities we haven't seen before. So really we want to say, really we want to say if city is in our city count dictionary and count is greater than 10. So here we're taking advantage of something called lazy evaluation. So what was happening is right here, we were asking for the city count of a city that wasn't in our data set, and that was throwing an error, right? If you ask for a key in a dictionary that that doesn't exist, then your Python interpreter is going to yell at you and be upset, right? It's like, hey, that thing isn't in here. So if you first check to see if it's in there, if it's not, because we use an and here, the rest of this evaluation will just not run and you won't get any errors. So if our city is not in there, we'll also default to state. And I believe we have 51 states in our test set or our train set, so that shouldn't be a problem. All right. We ran. Looks like no errors. So now let's just spot check clean train. Cool. And we have average city price. And now I'm kind of curious. Let's just look at what if we did a histogram of average city prices. Cool. That looks pretty sane. We could also compare this if we wanted to with before we cleaned it. No, actually, that wouldn't make any sense. Never mind. I'm being silly. But yeah, that's a reality check that looks pretty good. Thank you, Dark Rules, for the suggestion, because that is, I think, something that could help our model. And honestly, that's just a cleaner solution. Okay, so now we get to the big thing. So we have our training and validation set. Very nice. And so now we're going to pull out the big guns. So yesterday we talked about scikit-learn, and I think I mentioned this, is that scikit-learn, like one of the things that is really nice about it is that it is, sorry, if you see me continue to look over, my little dog Darwin, he's going through a little bit of a chewing phase. At least I hope it's a phase. And I'm trying to keep him just away from chewing on this chair. So I'm just pulling him close to me so he can chew on my foot instead. Okay, so we mentioned that scikit-learn is really awesome, but one of the reasons that it's awesome is because it's actually pretty easy to understand. And maybe you were here for the last term and you're like, I don't get that at all. Well, that scikit-learn was super confusing. In which case, fair machine learning, it gets deep, right? But TensorFlow is one of the two big libraries. I would say the two big libraries, PyTorch and TensorFlow, are two of the biggest sort of core machine learning libraries that people use. And they can get very technical and very deep into, running back the gradient tape and mucking with all your parameters, and that can get to be a little bit much for even for me, right? And so a thing that is really nice about this library, TensorFlow, is that it has a sort of companion library called Keras. That the way that I like to describe it is that Keras sort of turns TensorFlow into Legos. You get a lot of these individual Lego pieces that you can kind of just stack on top of one another and build yourself a cute little model without having to get too deep in the weeds. So TensorFlow is more powerful in many ways than scikit-learn, but Keras makes it not too much more complicated. So that's sort of the intro to TensorFlow. I don't know if anybody has any questions about TensorFlow or PyTorch or like why these libraries are more powerful. I'm happy to like go deeper on that. But maybe we just get in and take a look at it. So there are a couple things we're going to import. We still have this core idea of a model. So tensorflow.keras.models. And a sequential model is, earlier I was mentioning. Sorry, he's chewing again. Earlier I was mentioning that the Keras kind of lets us use TensorFlow like Legos, stacking one on top of the other. And a sequential model is just that. You just get a giant sequential stack of Legos, and your input runs straight through that, right? So you can swap out different parts of your stack, or make it longer, or make it wider, but it is sort of one sequence of layers. Then you can pick the layers that you want to use. Dense and flatten are two. I actually don't know if we need flatten, but dense is sort of a very classic for general problem solving. A dense neural network layer is a sort of a really general tool that you can use in a lot of different cases. In fact, most models, even when you're doing something a little bit more specialized, most models will end with one or two dense layers just because they are so sort of generic and kind of the Swiss Army knife of neural network layers. I don't know, we might, but I don't know that there's a lot of use in talking about different layers besides these two, unless they come up and we have questions. And then finally, our optimizer. So something we talked about yesterday was that our model has a certain number of parameters, and the training is when our computer sort of figures out how to turn those knobs the right way, right? So all of our parameters are these little knobs, such as, well, on average, how much does having another square foot benefit you? He's just really getting into trouble today. I apologize. And Darwin apologizes too. He doesn't mean to. Let's see, where were we? Oh yeah, so the actual machine learning in training is your computer figuring out how I should set all these knobs in order to get the best results. And we didn't go too deep on that, but it generally sets them, and then it sees how well it does, and then it sees, well, how could I have turned these knobs to do that a little bit better? So, maybe if the average price of a square foot was a little bit more expensive, I actually would have been a little bit closer to the right answer, and it can turn that knob. And so an optimizer is the chunk of your model that is really doing that math. So if you have heard of gradient descent or stochastic gradient descent, or RMS prop, root mean squared propagation, those are two kinds of optimizers. And then Atom is another very common optimizer. The Atom optimizer has been shown to work really well in a wide variety of cases. And so that's why we're using it here. So on to the pièce de résistance. So we have a sequential model, and ultimately what we pass into that sequential model is just a list of layers. So we imported our two layers, dense and flatten, and I will try removing the flatten. But we have a sequential model, and we just spit that out into a variable called model. So what do these layers do? Flatten, if you have an input that is a weird shape, so like a classic example of this is if you are dealing with images and your images are a three-dimensional matrix of pixels, and RGB values, then flatten just flattens them all out as if there was no structure to it whatsoever. which sometimes is useful. We might not need it here. I actually don't think that we do. And then a dense layer, if you've seen an image of what a neural network looks like, in fact, I'll pull one up right now. This is sort of the classic image of what a neural network looks like. So yeah, all of these are perfect. So if you see here, every single one of these input neurons is connected to every single one of the output neurons. And this is what we mean by density. There are just like a lot of connections in here from one layer to the next. That's true in this layer and in this layer and in this final layer. This final layer looks less dense just because there's only one output, so there's not, not lines crossing. But all of these are a dense layer. One thing that we could easily contrast this with is a convolutional layer. And so a convolutional layer might look like, well, what if we just look at these two neurons together, and then we slide our window and just look at these two neurons, and then slide our window and just look at these two neurons, and then slide our window and just look at these two neurons. So when you think you have some bigger structure in your data and you want to look at them together, or another great example of this is in language, right? You might have an intuition that that words that are close together have more influence on one another. Not always true, but maybe that's something you want to build into your model. You might use a convolutional layer. But a dense layer makes no assumptions, and it just says, hey, everything can talk to everything else. Let's see. Do you need to use flatten on vectorized images? So the short answer is it depends on how you vectorize them. But yeah, I mean, it also depends on what layer you're feeding them into, right? Because you might have several layers of convolutions, right? You could have a convolutional layer on a big image, and then a convolutional layer on a slightly smaller image, and you could keep doing that. And then at some point, you might probably want to feed it into a linear or into a dense layer, and at that point, you would want to call flatten on it. So we have one flatten layer, which, as previously mentioned, I think we can probably delete. And then 4 dense layers. So the thing about dense layers, or the thing about layers in these models, is that they only tell you, you only actually specify the output, and they just assume whatever the last previous layer gives them is your input size. So this dense layer has 1,024 output neurons. That feeds into another dense layer that has 664 output neurons, or output values. And then dense layer number 3 has 64 again. And then dense layer number 1 has an output of 1. Can anybody guess why we actually need this last layer to be an output of 1? This is not like a trick question. This is, relatively obvious. Why does the last layer have output 1? I'll give it a second. I also never know what the latency, both between you and Twitch, but then also Twitch and StreamYard is. So it's like, oh yeah, I'm saying something, and then 10 minutes later, not 10 minutes, but 15 seconds later, someone's like, oh yeah, this is my response to what you said. So the reason that our last layer needs to have this output size of 1 is that we're only predicting one number, right? The y val here, or the y values here, they're just a single list, right? So every time we're only predicting one number. And if you had 2 as the output dimension, then it would expect you to be predicting 2 numbers. And yeah, Kakaprog has it right, is that our label, it's just the labels that we're trying to predict are only one number big, right? So for everything that you're trying to predict on the output side, there should be sort of one output neuron. Right on. Cool. So then we make our optimizer. And so learning rate, we can talk about it a little bit faster. Yeah, okay, nanotubular also had the right answer. Yeah, that's on latency. So learning rate, so the LR here stands for learning rate. And this basically means how much are we going to shake things up every time we run through our data. So every time you do a forward pass on training, so this is you have your model try to answer all of the questions in your training data set, you generate a lot of errors, right? So some of the questions it'll get really right, and some of them it will get less right. And it will know something about, well, this is how I performed, and these are the things that I did badly, right? And so learning rate tells you, hey, based on how, like, what things you did badly on, how much should you change? And picking your learning rate is really important, because if your learning rate is too small, your learning process will just take a long time. But if your learning rate is too big, you can get into these weird positions where you sort of learn the wrong lesson every time and you kind of overcorrect, right? I don't know if anybody's had this in, I think it's less common for humans in like learning like math and science, but like I think sometimes people do this when they're writing. So somebody says, "Oh yeah, in your writing, like you don't use that many adjectives," and so then they go home and they write another essay, and the essay is like 80% adjectives, and like every noun, it's like the short, spry, lovely, furry dog cautiously walked judiciously over the verdant, green, beautiful, lush fern. And it's like, this is not, you learned the wrong lesson, right? You just needed to change a little bit, but you changed way too much. Sir Proud 69, good to see you. Good night. Take care. So picking a good learning rate can be really important for this. We might play with this a little bit, but we'll kind of see what happens. And then finally, our loss. Remember, the thing that we're trying to predict is, on average, how far away are you from the right house price? And so mean absolute error is the metric that we're using. So if we run this, we will get a model. And compile just says, okay, I've told you what I want the model to look like. Now go and sort of build it. This will take a second to run. And then we get a little bit of warning stuff. And this is, I mean, usually this isn't anything to worry about. I will say a lot of TensorFlow code that I have outputs warnings like this. Most of these are things that it's like, oh yeah, we're not using this particular plugin, but the plugin isn't there. And so TensorFlow is upset. One last thing that we can do here actually is call model summary. And so model summary will show us kind of what the internal guts of our model looks like. Oh, interesting. This model has not been built yet. We can compile it. Okay, time to do some live debugging. I feel like we did just compile our model. Oh, could it be Keras model summary? Print summary of the network. That looks right. I don't know if anybody can spot my issue here. But we are compiling it. Interesting. Model.build. Oh, not mode. Yeah. Okay, maybe we'll summarize after we've run it on some data. That is interesting. I guess we do need to specify an input shape if we want to run that before. Okay, so now we're going to jump ahead to actually training our model. So remember, training is when your model looks at all the data that it has the answers to. This is sort of like its study guide, and it tries to answer them all, and then it checks its work, and it sees how well it does, right? And then it can update based on this. And so every time it goes through all of the questions and tries to answer them, and then sees how wrong it was, every time it does that, that is called an epoch, E-P-O-C-H. So epochs right here is the number of how many times do we want to run through all of the data. And so in underneath the hood, scikit-learn was actually doing this for us. But this is one of those things that now we have a little more control over this, and it's going to be a little bit more obvious what's going on. So we pass it our X-train and our Y-train. So that's actually what it's going to be learning from. And then we can also pass it our X validation and our Y validation. And so every time it does an epoch, it will actually check with this and see how well it's performing on our validation data. Then we can also grab Matplotlib and actually plot the history of how well it does on the training and how well it does on the validation. So that is what this graph is doing here. We can hit that and we can see what happens. So you can see as it's running here, you can see this is the training loss. And then on the right-hand side, this is the validation loss. So you can see generally This is going down, right? Generally, it's tending towards lower numbers. Okay, cool. So now we get this graph. And great, relatively good graph to make sense of. So our training loss is in red, and our validation loss is in blue. So a couple notes. One is usually, well, oftentimes your training loss will be better than your validation loss. This would be to say that your red line would be below your blue line. In this case, it doesn't seem to be true. And one reason that could be is that if our validation test or our validation set just happens to be a little bit easier. So if there are sort of hard cases, sort of like anomalous or weird houses in our training set, then that's one reason that it might perform worse on that than on the validation set. But the other thing that's really important to look at is that the validation loss is a little bit noisier, right? It seems to go up and down a little bit more chaotically. So I want to try a few more things here. One is actually want to make our model bigger, mostly just to prove a point. So what if we jump up to 512 for our middle layer here? And then let's make our learning rate a little bit higher as well. And let's now, instead of 20 epochs, let's train for 30 epochs. And this first, I guess, the biggest thing that you could probably see relatively quickly is that the training is taking a longer time. And this is that moment where I'm like weighing the, oh yeah, I really want to show you what happens when we do this with the model. And also I don't want to just, have sort of dead time on stream. Maybe it's time to play for you the bird song. Maybe the next long model we train, I'll pull out the ukulele and play some ukulele for you. It's going. It's thinking about it. And you can kind of already get a little bit of a picture of how this is going just from the log here. But definitely nice to graph afterwards to just really see kind of the story of what happened. Oh, also now that we have actually run it, we should be able to call model summary on it. It's getting there. Okay, cool. So here again, we kind of see some bumpiness. And you see some sort of more bumpiness in the validation than in your training data, which, that makes sense. You also, I mean, this is a thing that is sort of interesting, is that you do see the line, like, it does still look like it's actually trending down. And so you could even imagine, well, hey, maybe running it for another 10 or 20 epochs, like maybe that would actually be helpful. And one more thing actually that I want to throw out. Oh, actually, one thing that we should try actually is switching to accelerated hardware. So one thing that's awesome about Kaggle is that they will give you GPU time for free. And if I remember correctly, this actually should. I don't actually think you need to specify the device with TensorFlow. I think it just figures it out for you. That might not be true. I'm gonna have to set the device. So we are now spinning up an environment that actually has a GPU in it. Excuse me. Cool, our session has started. You can see now we have a GPU that we can see our consumption on. Most of this should be relatively fast. What's with the data? If you overfit on training data, the validation loss also decreases. I've seen this happen before. I am not 100% certain what you were talking about. What's with the data where if you overfit on the training data, the validation loss also decreases? So generally speaking, if you're overfitting, then when you look at validation or test performance, like that'll get worse. And there might be a little bit of weirdness here just linguistically. When you say the loss, like when loss goes up, that means things are worse. And when loss goes down, that means things are better. I mean, I suppose there are like really, if you quote unquote overfit, but it still does well on data it hasn't seen before, then I made the case that maybe you haven't actually overfit. This becomes a little bit of a tricky thing. That's like, well, hey, maybe your validation data isn't that good either, right? Maybe your validation data has some artifacts to it. Okay, so this was taking like 8 milliseconds per step and like 5 seconds per epoch. So if that is faster, then that might be a sign that we're actually effectively using the GPU. Okay, there we go. Yeah, so this is, I mean, about half the time. Interesting, our first epoch actually took a little bit longer, but then after that, it looks like, yeah, like two seconds per epoch. So one thing I was kind of attempting to do here was, oh, can we make the model so big that we do actually kind of overfit? And there certainly are, are ways to do that. I'm just considering like, oh yeah, how do we push it into overfitting territory? And I mean, the classic ones would just be to give it more parameters, right? So we could make this first dense layer actually 2048. And maybe we actually delete this one just so it doesn't take a gajillion years to run. Actually, maybe we do leave it. Maybe we leave it like that. Has this finished running? Okay, so here even here you can see now the validation loss is like a bit bumpier, right? Okay, so let's run this. This time, let's only run it for maybe 15 epochs because this will actually take, I would guess, quite a bit longer. Even though we're using the GPU because our model is so big. Didn't take much longer, actually. Okay, yeah, still pretty fast. But just purely for demonstration purposes, I'm kind of curious. Oh yeah, can we make our model big enough that it really does start getting that conspiracy theory brain? The other thing is, oh yeah, if we're only running for 15 epochs, like, yeah, there are cases where you just need to train for longer and then it overfits. So definitely actually like not training for that long can be a super valuable way to avoid overfitting. Okay, yeah, there's a little bit more of like craziness. You get cases where you're performing much worse on your validation data than on your training data. Let's do one more bump where let's bump this up to 20 or 1024, and then let's in fact run for 30 epochs. And maybe this will take long enough that I'll pull out the ukulele. Okay, cool. We should have a few minutes or a minute or two maybe. So there aren't too many people that I think have been to previous tracks that I have done. But there is a song that I actually don't remember the origin of it, but it was inspired by the first Global Hack Week. That is its origin. And it is a song about the truth about birds. Here we go. Okay, let's zoom out so you can actually see the ukulele. I am so unsure about so many different things that I have heard, but there's one thing of which I am certain, that the US government invented birds. They are fake, you can see it in their eyes. They're the NSA's favorite little spies. But there's one thing of which I am certain, that the US government invented birds. Stay woke, sheeple. Oh, thank you, the Grinch watches. That is, along with the flower crown, it feels like it's not actually Global Hack Week if I don't do that. Okay, back to our model, which hopefully has finished training and hopefully will give us a good example. Ooh, okay, so this is interesting. In a lot of our previous ones, we have started with relatively high error, like around the 9,000-ish area, and then we've come down. This is a case where we actually started with pretty good error. And one way that I'd phrase that is sometimes you kind of get lucky, and the random parameters where you start at are actually pretty good parameters, and you can train relatively efficiently. It probably also helps that our learning rate is relatively high. But here you can clearly see that, yeah, like our validation loss is not really improving here. We also don't have, like, our data is not actually that complex, and so this size of model likely is actually overkill for us. So one thing that I might recommend is seeing if we can make this smaller and still get good results. So one thing we could do is actually just remove that middle layer, maybe knock this down to, like, I don't know, maybe even 256, and maybe we knock this down to 32. So we've just made our network just like wildly smaller. And let's make our learning rate actually lower as well. Let's knock it back down to 0.01. And let's try fitting it again. Let's see what happens. And now this actually should be relatively speedy to train. Yeah, it's like a second or two per epoch. I really should have taken notes on what we did earlier, because I'm modeling bad behavior, because when you're doing, when you're doing this sort of iteration where you're testing different things, you really should keep a log of, oh, this is the model that I used, and this is sort of the performance that it got. So as we continue to iterate, I will be sure to save performance numbers. Let's see, what was I doing down here? Doing better over here? No, that does pretty bad too. Oh, that's super interesting. Huh. Now I'm kind of kicking myself because I have a vague memory of actually getting better performance with the neural network here. Maybe it was zip code. Maybe we used zip code. Maybe zip code was more useful. Okay, so we see some decent. If I recall correctly, this is actually about what we did with the much bigger network. And so all that extra compute and the extra time it took us to train wasn't actually improving things much. So coming back up to the data that we're using, I'm actually now curious, what if we do switch back away from city and to zip code? So everywhere where we're doing zip code things. And maybe instead of 10, maybe we lower that threshold to like 3. As long as we have 3 zip codes, we still count it. And this will be get average zip code price, zip code, and zip code counts. And then we can still do the default to state. That seems fine. And we'll come back and replace that with city. Then in our apply, we'll call it average zip code price. It probably also wouldn't hurt to have both of these here. Let's see if that runs. Did I have any bugs? Just thinking about it. Oh, I had some bugs. Average home prices by zip code is not defined. Oh, yeah, this needs to be average prices, home prices by zip code. Cool, looks like that ran. And let's just give this a go again. Let's see. Oh, so actually we'll record. So we had our last validation loss, 73,000. Oh, we should actually be able to run. No, we rebuilt it. Never mind. We'll try that again later. So we'll call this with city without zip code. And what was the size? It was 256 and then 32. 256, 32. So just some general notes so that you can remember sort of what kind of model you were using. And then we try again. You can compare. Ooh, okay. We've broken 70. That's good. That seems powerful. This right here, this is actually what a lot of machine learning is just staring at your performance numbers and being like, oh, go down, go down. Okay, cool. 63,000. So we could call this with zip code without city. Same architecture, 256, 32. And our performance considerably better. We might as well also just try, what if we also add in zip code? Or no, what if we also add in city? So let's we just copy this and do it for cities. So average home prices by city. Cool. And then we can copy this as well and say get average city price. Nice. And yeah, we can default to state as well. Cool. You could also we could do a little nesting. We could say, okay, if you don't have zip code, default to city. And then if you don't have city, default to state. I actually kind of like that as a method. So we can replace this and we'll just pass in the whole row. So now we can use get average city price and throw it in here in exactly the same way. You can call this city price, get average city price. And we'll have to drop city down here. Any questions or thoughts on this? We're just kind of, we're iterating with, well, what variables do we include in there? We can generate our split. And we'll see where we get. Okay, we're getting somewhere. We've broken 70,000, which is good. We still got about 10 epochs to go. See, how about different thresholds for city versus zip codes? Yeah, that seems, to me, that seems super reasonable that like, oh yeah, zip code we know is a pretty targeted thing, so maybe there are only a few records in there. But a city, like, you should have, maybe 5 records in your city. I mean, that doesn't seem crazy to me. We could give that a shot as well. Okay, so this validation loss actually worse. I mean, you can see it's bouncing around a little bit, and so maybe you don't want to put too much stock in that. But this kind of seems like having zip code and city, or with zip code and city. Actually did not lead to better performance. Which we weren't actually tracking training loss, but usually you would expect training loss to still go down. There is also, of course, a little bit of randomness in all of this, so you could add a random seed, which maybe is something that we should do. But yeah, we're just iterating here. Well, let's try this suggestion of, yeah, maybe city should have a higher threshold that if there are only 3 things in your city, maybe that's too small of a city to really learn something about. Okay, already it looks like we're maybe making a little more progress. Would I call this feature engineering? Yeah, that's a good question. Maybe a little bit. There's maybe a subtle line between feature engineering and feature selection. One way of thinking about it is the more features you put in there, the sort of more opportunities you're giving your model to overfit on training data. But yeah, I think feature selection, feature engineering, kind of a fuzzy boundary, but for sure. Okay, so that also, this is with zip code, with city, higher threshold. Better, but still not as good as just with zip code and without city. So why don't we just get rid of city? Yeah, let's just remove our city stuff. Oh, actually, let's leave all that stuff and just not include it so we can still default to city for zip code, because that's actually kind of nice. But we just won't add that. Right on. Okay, so now we could lots of next steps we could take. We're kind of getting marginal improvements here, but we could try doing some hyperparameter search. So the normal way that you would do this is you would pick something you want to tweak. So like maybe it is the size of our middle network here of 256. And you could say, well, hey, let's try this at, in a loop. Let's try it with 256 and with 512 and with 1024 and with 2048. And that would like help you hone in on the right thing. I do actually, okay, Jackson recommending, there are actually a lot of very neat Python packages that do a certain kind of feature engineering, feature extraction for you. A lot of really cool ones for time series analysis, where they will, like hone in on like actually like the third derivative is really useful here and stuff like that. Which we could get into that. Maybe that is for another stream, another time. But yeah, there are lots of, I don't know, is there is the package called feature tools? Feature tools, automated feature engineering. There you go. Which is kind of funny to me because, and this is, I mean, we're being a little bit selective here. People often refer to artificial neural networks as doing automatic feature engineering, right? Because they kind of can pick up on nonlinear relationships and say, well, what if we put these two things together? which I'm sure that is a thing they're aware of with their branding. But very neat. So yeah, we could try different shapes just to play around some more. We could actually, one thing that feels worthwhile is just really letting it run out and seeing, instead of 30, what if we do 100, and just see where that lands us. We actually need to recompile. And because our model is relatively small, we might not worry quite as much about the limitation, or about overfitting. But we'll of course see how it does on validation. And we'll see at what point does it really stop getting better, because sometimes these things do actually just take a really, really long time. We could try leaky ReLU. Yeah, no, that's fair. Different activation functions. Yeah, that's actually not something we talked about too much, which maybe that could be fun to chat about. Okay, so activation functions. This gets a little bit into. I hesitate to say I should talk about how artificial neural networks have a biological basis, because artificial neural networks are only rooted in sort of neuroscience, only in sort of the vaguest way, right? There is this idea that in our understanding of the brain, you have these neurons that have all these dendrites that accept sort of inputs from other neurons, and then they look at all of their inputs and they say, "Do I fire? Right? Do I have enough input to send off a signal?" And the decision of do I send off a signal or not, that is really what an activation function is sort of tasked with emulating, right? And so on some level, it has to be nonlinear. You can't just have a single linear transformation. Otherwise, your entire neural network would basically just be one matrix multiplication. But there are lots of different ways that you can make that decision on the boundary of do I have enough potential coming in to send off a signal on the other side. And so one very classic activation function that people will use is the sigmoid function. We can look at an image of. Boom, there's your sigmoid. And that is basically, if the numbers coming in are pretty negative, it will send off very little output. And if the numbers are really high, it will top out at around 1, right? Actually, not around 1. It tops out basically at 1, right? Never touches it because it's an asymptote. And there is another activation function called ReLU, which is rectified linear units. And that looks like it is just totally flat if you're less than 0, and then it is a straight line if you are greater than 0. And this is another one that we actually find to be relatively effective in a lot of cases. And then you have leaky ReLU, which is I'm not. I know specific cases where they're like, yes, like we tried ReLU and like it did better. Leaky ReLU I actually know less about, but this actually gives you all negative numbers are the same for ReLU. They all just map to 0. Whereas a leaky ReLU says, okay, like maybe if you are negative, you'll be close to 0. But if you're really, really negative, maybe we allow some negative information to leak out, basically. And you have some coefficient that sort of reduces the impact of negative numbers. And I believe we could just test that out to see if leaky ReLU does better just by changing our activation function. Okay, so you can see we do, even after a long period of time, we're still making a little bit of progress. So one thing you could say is, well, hey, should we run even longer? And yeah, you could. You might also say like, hey, should we have a slightly higher learning rate? And that is something that I would try. If it seems like even after a long period of time, you're still making some progress, trying to bump up your learning rate is something you can give a shot to. So why don't we try leaky ReLU? Is it just leaky ReLU here? Does that work? Or is that a special? Let's see. Nope, it doesn't like that. Let's see. Leaky ReLU Keras string. Okay, it does. It looks like you actually have to. Yeah, it looks like there's no alias for leaky ReLU. So we'll create our own leaky ReLU. Cool. Layers, leaky ReLU. And sure, let's try an alpha of 0.05. So we'll actually remove our activation function from here and add another activation layer that does the leaky ReLU transformation. I did forget a comma. Thank you, Python interpreter. And let's drop this down because we want to save some time. And let's say, let's go down to 30 epochs again. That seemed like a good. Oh, I can type. I promise. Is your learning rate 0.001? Learning rate is 0.01. So is that 1e minus 2? Yeah. So we could imagine making our learning rate higher or lower, really. So oh, I actually really should have gotten a better point of comparison. I guess we still have, this is the same basically. So without city, it was 63 was where we topped out after 30 epochs. Yeah, looks like leaky ReLU is not actually better. Now, this is I'm saying, oh, it's not actually better. Really, if you wanted to know this, you would want to run this several times, right, with randomized train test splits. Oh yeah, Keras is great. Keras is in another. If we had a fifth session, I would go into that. You can sort of automate your hyperparameter tuning search, and so you can see, what are the best architectures and what are the best learning rates, and what all the parameters that you have. How can I set these better? Cool. So one other thing I want to try, just because I actually saw that it has gotten some relatively good performance, is actually moving away from artificial neural networks. Not because I don't like them, but because sometimes they're just not the right tool for the job. And trying decision trees and random forests, which had gotten some love, and seeing if, just because it would be great to get some good. Actually, before we do that, let's actually take our best. I think this will have been sort of our best model so far, and let's kick it up actually to 100. And then actually use this to make predictions. Oh, I thought about it. Cool. Oh. Okay, this was the delivery. I will be right back. It's okay. You look sweet. I just got attacked by a mean old dog over there. Oh no. Yeah. Oh gosh, I'm so sorry to hear that. I thought she had a wolf thing. Yeah. She did. I went to the yard. So bark at me. She took it around the corner. There's a bunch of apartments outside the gate. Then all of a sudden the dog comes running around the corner. Oh yeah, you growled me too. Okay, yeah, everyone just do it. Super intimidating. Yeah. Okay, y'all. Apologies for the for the interruption. God bless Darwin. Yeah. Yeah, Darwin really does love other people, but he does not like it when people come to the door, you know? People coming to the door, his least favorite thing. But he's chilling out. He's chilling out over time. Okay. So we're back at it for maybe a few more things to try. Maybe we get some better performance here. And yeah, we still tap out around the same place. But we'll get a graph in a second to confirm that. It's thinking. It's really thinking about it. Ooh, okay, very cool. So you see, it's kind of a bumpy road, but we do improve over time, and it does seem like we're still consistently improving. But our validation gets super bumpy, right? And so it's like, yeah, maybe when we try it on data we haven't seen before, we'll get sort of between 64 and 66, but maybe we'll get like 71 if it's up here. So we don't have as much confidence in this. But I think it's worth giving it a shot and then trying one more thing and then closing out. Okay, so here is our summary. You can see we have both the different shapes of things and then also our number of parameters. So you might be saying, hey, Will, like, where's 3,000 parameters coming from? And the answer is it is coming from multiplying 11 by 256 and possibly including a bias unit there. And the cool thing about this is, I think, especially now that large machine learning models are sort of in the news all the time, people use as a really rough metric of how powerful something is the parameter count, right? So I'm sure that, well, perhaps you have heard that that GPT-4 had over 100 billion parameters or over a trillion parameters. And on some level, these numbers don't mean that much because the data you were trained on and your architecture and how long you were trained, all of these things have a really big impact on how good of a model you are. But it's just a raw metric of, well, how big and how much capacity does that model have? Parameter count does tell you something. So our lowly model here has 11,000 parameters, which is not as much as GPT-4, I feel confident saying. But so now we have a model. And so now we could use this to predict on our test set. So if we come and we grab, let's see. I'm going to grab this as sort of a template for prepping our test set. Actually, let's just put it up here. We won't have a Y for it. X test can just be clean test, and we can remove that. And we don't need to drop price because price isn't there to begin with. Now this we should actually just be able to pass into our model and predict on it. So we should just be able to say model.predict. And then we'll come back to our test clean test, and we'll say price equals our prediction. And it predicts pretty fast. Cool. Yes, I was in fact thinking of using a like XGBoost. I'd probably just use that. I think there's an XGBoost implementation in scikit-learn. Yeah, you got me. Let's see. Can those numbers get repeated? I'm sorry. This is the latency when it's like, yeah, several seconds after I say the thing. What number's getting repeated? Cool. So now we look at clean test again. We have our price that we actually wanted to predict. And we should be able to pull out of that ID and price. We can call this submission. And we can just say submission.toCSV. Oh, submission.csv. And I think we say index equals false. And the rest of this, I'm just going to comment out. So now, if we just come over and make sure we have that file in our output, we should be able to submit this and see what happens. Kaggle working. Boom. Submission.csv. All right. Let's try submitting and see what happens. And this also will have the impact of publishing it, I believe. So you should be able to see all of my updated code now. Cool, cool, cool. Okay, so while this is running, and this should actually take a while to run, I actually want to come back and try one more thing. So a lot of times a neural network, it's fun to try out and it's fun to throw it in there because it's, I mean, mostly I just wanted to show, hey, you have scikit-learn, this one library, but there are other libraries that, that do other kind of cool things. But a lot of times for tabular data, a simpler model can actually work better. And in some cases, generalize better. So let's come back to our competition. And you're welcome to click new notebook along with me, or you can catch up when I publish this. Call this part 4.5. And actually, before I even give this a title, let's go to the scikit-learn and look up gradient boosting. Gradient boosting regressor. Okay, cool. So what is gradient boosting? Actually, now part of me wants to do just like a simple random forest first. Let's just do gradient boosting. So we've talked about lots of different kinds of models, and on some level, the underlying model doesn't matter that much. Oh, don't like that. On some level, the underlying model doesn't actually matter that much. You can imagine a linear regression like we did on day 3, or like a neural network like we're doing today. You can also think of a decision tree if you are familiar. It's kind of like a little flow chart where you ask like, well, if this is true, then do that. And if that's true, then try this other thing. And you go down your decision tree. I think in practice, they use decision trees in this implementation of gradient boosting. But so the idea behind gradient boosting is to take a model and make it a pretty weak model, right? Take a really, it's kind of like our model with linear regression where we just used living area, right? Take that and see how well it performs on your data set. And then find all the cases where it performs really poorly and take those examples and train a new classifier or a new regression model just on the cases where the first one did badly. And you can repeat this process. And you can say, okay, this second model is now like an expert in some other things. What things does it get wrong? And then take just that set of things that it gets wrong and make another model and just train it on those cases that are sort of hard. And so you go through this process of training one model and seeing what it's good at, and then creating another model and seeing what it's good at, and then training another model and seeing what it's good at. And you end up with sort of this cohort of a lot of things that are experts in different cases. And then you basically take all those models together and let them vote. So this is an example of an ensemble model where you have lots of little models that are kind of all figuring out their own thing. And then you sort of bring them all together to try to perform better than they could do apart. And this is, in a lot of tabular data tasks, like a kind of gradient boosting can be really, really powerful. So popping back over to my screen, actually first checking what Ajaxon said. Gradient boosting ensembles beat me on Kaggle every single time on tabular data. Yeah, it is. On some level, I don't want to say it's unexciting, but like the number of things that library or the gradient boosting in general can just do really, really well. Honestly, upsetting sometimes. Yeah. So we have sklearn ensemble gradient boosting regressor. And one of the things that I love about scikit-learn is that they usually, if you scroll down long enough, they have an example of just how to use this thing. So here's our input statement. We'll pop over here. So I'll call this gradient bow. Nice. Gradient boosting regressor. This should be code. And it's starting up. And so we will just create our regressor. Oh, I don't know what you can see, but I accidentally just logged out of my laptop. I blipped out of existence for a second. I apologize. So we'll make our gradient boosting regressor, and then we can fit it on our data, and then we can predict. Cool. We will need to come back over here and, okay. So you can see we actually, and this is kind of expected, but we actually, again, got worse on our actual test than when we were doing our cross-validation. Which is sort of another sign that, like, oh yeah, maybe the test set is actually in some ways a little bit harder or a little bit of a shifted domain than the training set. But we're just coming back here. We had our little dalliance with artificial neural networks. It's fun. Artificial neural networks are fun, but we have other things to do. So let's grab our data again. And we can grab this too. Why not? Anujian asks, is it necessary to use gradient boosting model? Not necessary. I think the thing that is always fun about Kaggle competitions is just the number of different models, a number of different ways that people will use to approach the same problem. I think that is like a super cool feature. And seeing these notebooks that people release of like, yeah, like I used an SVM to do this task, or I used a decision tree. That diversity is cool. In terms of what might be the best model, I mean, we'll see. We'll run this and we'll see how it does. But yeah, I think as Ajax was saying, like, yeah, the gradient boosting often happens to do pretty well in cases such as these. Okay, cool. Looks like we imported. Did this run successfully? Maybe, hopefully. Then we have our gradient booster. And then we can just copy the way that we split up our train and validation and test. And actually, this actually should be fast enough. Let's not even deal with validation. Let's just use all of our training data and then just submit it, because that should be relatively quick. We can actually copy our submission stuff as well. Okay, what did we get wrong here? Oh, we did clean train, not clean test. Maybe that works. And let's just submit this and see what happens. Scroll down to grab our submission code. Boom. A thing that is both I think like fun and good to demonstrate, and also can be a little depressing, is like, oh yeah, we spent like an hour sort of messing around with artificial neural networks and like kind of getting okay results. I would say like the results were not terrible, but they weren't awe-inspiring, and and then switching to, you know, a relatively, I mean, comparatively a simple model like gradient boosting. And, you know, that was maybe 5 minutes of coding. And, you know, we could be a long way off. Maybe this actually will not actually perform that well, which I'm open to. But let's see. It already scored. Let's see how we did. And yeah, that's one of our better scores so far. After 10 minutes. And I'm sure, could mess around and tweak with this to get even a little bit better. So let's look at the. We'll tweak just a touch, and then we'll wrap things up. So what kind of parameters do we have? One of the big ones is the n estimators. So this is sort of the number of different models that are going to be in your ensemble at the end, right? If this is a random forest, I would say this is the number of trees. So this is the number of sort of individual experts that you're putting together. And so we certainly could crank that up to a higher number. Yeah, looking around. Yeah, let's try just cranking up n estimators and see what happens. Oh, the other thing that we should actually do is we should change our loss to absolute error. This is actually this is kind of a big thing that we can talk about. So in stats in general, there's an idea of squared error and just absolute error. And so the idea with squared error is you take however far you are away from the right thing, and you square it. So if you are off by 1, that still ends up being 1. But if you're off by 2, your error is now 4. And if you're off by 10, your error is now 100. And the impact it has is really, really penalizing things that you are further wrong on, right? It's like you'd rather be a little bit wrong about everything than perfect on most things and really wrong about one thing. Mean error or absolute error is a little bit more forgiving. It says just in aggregate, we want to know this is accurate. But if every once in a while you have sort of like one really bad guess, that we're going to be a little bit more forgiving towards that. And so the fact that our regressor was actually using squared error means that it was going to be making a trade-off about, well, hey, what do I do for this case where I'm weighing between getting multiple things a little bit wrong and getting one thing really wrong. And if we tell it its loss is absolute error, it should perform a little bit better. So into our gradient boosting regressor, let's say loss equals absolute error instead of squared error. And then let's say n estimators is equal to, instead of 100, let's crank it up to 1,000. Let's see what happens. And we'll just make sure that runs, but then try submitting it again. You can also notice, actually, it takes a decent longer time to run with 1,000 estimators than it did with 100, because, I mean, obviously we are increasing the number of estimators by a factor of 10, right? Cool. Okay, that didn't take too long. So let's try submitting. And I think we'll see how this does, and then we'll do sort of a final check-in, and I'll leave y'all to it. I guess I don't know what word I'm looking for, to sort of get these out early. And any final questions that folks have, either about what we covered today or this week or the competition in general? It's thinking about it. And oh, is that our submission? Did we finish? Interesting. We did a little bit worse. I suppose the guess there would be that that we had too many estimators and that potentially we were overfitting a little bit. So I know I said that was going to be it, but now this is, you get into the cycle of like, oh, let's test that out, So probably we should at least try knocking back down our number of, expand our number of estimators. What if we just go down to 200? I should run like relatively faster. Cool. Oh wow. Okay, deep cut. I feel about that because sometimes I remember usernames from several times ago, but I'm so glad that you were at Global Hack Week December and enjoyed it. Let's see. Global Hack Week December. That wasn't credit card fraud, was it? I'm trying to remember what I did in December. I should go back and check. Okay. Last submission, I promise. Thinking about it. The last one took 3 minutes to submit, so okay. Huh. Still around there. I guess at that point, I would guess either there's some random variation, and we're not trying we're not iterating enough times to kind of reach some kind of stability, or again we have more models than we need in our ensemble. So you could try going down to 100, or alternatively, for whatever reason, absolute error is actually performing worse, which would be surprising to me. But maybe that is an exercise we leave to the reader, and y'all can play around and figure out. So this is the one that was getting 6,800. But now I'm just thinking it's okay. This is really the last one, and this time I mean it. Otherwise, I will just revert it back to the thing that was getting 68,000, and we will call it a week. Is it a good idea to pre-process truly test data with the same pre-processing we did on trained data? Yeah, I mean, so generally, I'll say that you definitely have to be sort of careful about this, because there are definitely a few things that we do in our pre-processing that could bite you. Like, for example, we have to handle the case where, we do something based on what city you're in. But if there's a fresh city that we've never seen before in the test set, that can throw things off completely, right? So things like that, where your information that's truly out of domain that might be in the test set that is not going to be in your training set, that's something you want to be really careful about. Besides that, yes, generally you want to do the exact same thing to your test set as you've done to your training set, because otherwise that'll be a source of difference that your model won't necessarily know how to take account of. Okay, there we go. So that is so far our best score, and it's not the top of the leaderboard, but it's up there. Okay. I will grab the link of the December stream because I'm super curious. But why don't we? I guess this has now been published. It should be publicly available under code. There you go. It looks like that probably should update when it gets the new stuff. But already there are lots of other things out there that are doing pretty well. So maybe you don't even want to copy my notebook, which honestly, the point where yes, the community is producing enough good sort of starter content, like that's a dream. Let's see. Otherwise, I trained a model on a column price per square foot, and I realized that it is overfitting. Is it overfitting? I'm curious what your rationale is for why it's overfitting. I mean, certainly if you have just the number of square feet in there as well, then yeah, that would be like it'd be giving your model an opportunity to overfit. I guess there's sort of the difference between, oh yeah, have you set up the conditions for something to overfit versus has your model actually overfit? And that definitely comes down to, oh yeah, does it perform poorly on data it hasn't seen before? I think is the main thing. But all right, party people, I think we'll do a short recap, answer any remaining questions, and then we will wrap it up. We have this week done a lot of fun, interesting, cool machine learning work on predicting housing prices. We learned, we refreshed our knowledge of Python. We got into exploratory data analysis and explored the relationships inside our data. We built some simple models with linear regression, and then we built some more complex models with artificial neural networks and TensorFlow and Keras. And then we sort of rounded it off with something in the middle with gradient boosting, and so far have gotten some pretty good performance. There's also been some incredible contributions from the community to sort of finalize what we're doing with the competition. There are 5 prizes we'll be giving out, 5 swag drops. First place and second place, self-explanatory. One will be raffled off from all of the remaining participants who have submitted, and then 1 prize for discussion and 1 prize for code contributions. So good reason to submit, good reason to share your code, and good reason to contribute to the discussions. Right on. I think that's where we're at. Dark Rules has another question. Oh, because I can't test. Oh, okay. I see what you're saying. If you were actually taking in your test or in your training set, you are using price to calculate price per square foot as a feature. This is actually a thing that's called leakage, where you are including information in your training data that you won't actually have when you are testing. And yes, because you already have in your training data the number of square feet, that if you include price per square foot, then you're actually just including the answer in your question, right? That you can just trivially multiply price per square foot by the number of square feet. I was thinking you were maybe doing just overall, or price per square foot in your state, or things like that, which those, could be useful. But no, I see what you're saying, and you're absolutely right. And the word for this in machine learning is leakage, when you include data in your training set that won't actually be available to you when you're testing. All righty. Any final questions before I play some Kalimba and send y'all out? Let's do it. All right, thank you so much for being here with me this week, friends. Happy Global Hack Week, and happy hacking. Ooh, can we get Appa as the next MLH mascot? I like this idea, although I think you'll have to wait because they always do the letters, and I think we're past F. What is it? I think we're on. Is it a file system? File system ferret was earlier. But yes, once it wraps back around, I will petition for Appa to be the MLH mascot. All right, thank you all for being here. Really appreciate seeing you stream after stream. Happy hacking, and then I'll be back on Discord to announce the winners probably on Saturday or Sunday. So I will see you then. Peace, y'all.